But so you need a filter that is 10 kilohertz divided by 580. So this is about 1 in 58. Maybe it's about roughly 2%, right? 2% bandwidth. So if you want to have a filter, that filter is quite narrow band. So the idea of electronic engineering is to convert this frequency to a lower frequency. So what you do is that you have this received signal, which is the original voice signal multiplied by the carrier frequency. Okay? And then you have it coming in, and then you send in a frequency at the local oscillator frequency. LO is local oscillator. And you can change this frequency. And what comes out here is that you have omega intermediate frequency, which is omega LO minus omega carry. Okay? Then you send this through a pass band filter. You send this through a pass band filter. So what happens is that at this stage, this frequency can be taken down to a more lower frequency. It might be taken down to an IF frequency. Maybe say if we are lucky, we can take it down to 50 kilohertz. Okay, this is IF. If you can do an heterodyning system, we can take it down to that frequency. That frequency is still above the hearing ability of the human ear. So that's why it's called supersonic heterodyning. The process of changing the frequency to a lower frequency is called heterodyning. And say if you now design a filter that is 10 kilohertz in bandwidth, then it's 10 over 50. And then it's 1/5 is about, let me see, 20% bandwidth, right? So you can work with a much lousier or worse filter, and yet you get to discriminate one station from the other one, yes?
So the signal coming out of that X thing is f of t cosine of omega IFT?
Whatever comes out here will be this one shifted. Okay, it's a product. You multiply by cosine of omega LOT. So it will be the product of these two. And so it will be further modulation by this oscillator frequency. And you can change this omega LO by a tuning, by a knob. Okay, you can have a knob to tune this omega LO. So depending on what radio station you want to tune in at, okay, you will get that radio station to go into the omega IF. This is omega IF zone. And then you work with much lower frequency. You can work with a much lousier bandpass filter. Okay, this bandpass filter can be 10% bandwidth, or in that case, 20% bandwidth, rather than 2% bandwidth. It's very hard to design a very narrow band filter. It costs a lot more money. Okay, that is the primary reason for super heterodyning. Another reason is that it is much easier to design low frequency electronics than high frequency electronics. I do not know if you have worked with any electronic designs. If you have to design electronics at 580 kilohertz, it's a lot harder to do compared to designing electronics at 50 kilohertz. You will learn that as you progress in your electrical engineering courses. Okay? So that is the primary reason why we need to super heterodyne. Are there any questions regarding this? If no, let's move on to a new topic. Let's move on to chapter 9 and study convolution. I think a lot of you asked about what convolution is, and today we'll learn about what that is. It's actually a very wonderful and interesting property in signal processing. Okay? No questions, then we can proceed ahead. Okay, here, if you do a bandpass filter, you will have something that's proportional to cosine of omega IF. And you can do envelope detection, phase coherent detection, and all kinds of detection by working at a much lower frequency here. Okay? And then you can go through all kinds of processes here. But If you do not have any more questions, let's talk about convolution. Convolution is defined to be if I have a signal f of t, I can convolve it with another signal h of t, and the resulting signal I can call my output y of t. And this is usually indicated by a star signal. And let me see what this star means. This star means you take this signal and this signal perform a kind of interesting integration. You multiply these two functions together and perform a very interesting integration. And the integration can be written in this form. Okay, that's what the star means. Okay, just multiply two functions and then integrate over tau. And then this, apparently after you integrate over tau, is just a function of t. Okay, but it doesn't matter how you write this, because I can also call this, do a change of variable, call this tau prime is equal to t minus tau. I can do a change of variable, then the tau prime is equal to minus the tau. Okay, and then I can rewrite this thing as being equal to f of, in this new variable, tau is equal to tau t minus tau prime. Okay, with this change of variable, you can see that tau, the old tau is t minus the new tau, or the tau prime. Okay, so I can rewrite the first thing as t minus tau prime, and then the second function is tau prime, and then the tau is just minus the tau prime by the change of variable. And then the range of integration will be flipped, right? The range of integration will be flipped with this change of variable. Tau equals minus infinity is tau prime equals infinity. Tau equals infinity is the same as tau prime minus infinity. So this range of integration will go from infinity to minus infinity. But I have a minus sign coming from here. I can use that minus sign to flip this around and get this integration to be that. Can everybody follow? Or you want me to repeat that? So this integration is exactly the same as this integration by the change of variable. Okay. If I define convolution to be that, I can change the order of these two and call this to be ht convolved with ft. So order is unimportant, as you can see. You take two functions, whichever comes first doesn't matter. If you define convolution to be this way, then this convolving with that will be that way, and you can show that the two integrations are the same. Okay, so order is unimportant, as you can see. So you can actually be cavalier about what order it should be. But what is one important property of convolution? One important property of convolution is Fourier transform. If you were to Fourier transform y, it has some very interesting relationship to the Fourier transform of f and the Fourier transform of h. Okay, let's see how that comes about. Okay, let's assume that h of t has a Fourier transform given by this quantity over here. Okay, that this Fourier transform exists, and that this Fourier transform also exists. And let's substitute Fourier transforms, those Fourier transforms into this integration. Let's see what we get. So y of t is equal to minus infinity to infinity f of t, f of tau I mean. And then let's substitute ht minus tau with that Fourier transform over there. Okay, if I do that, then I will have 1 over 2 pi minus infinity to infinity d omega e to the j omega. And what should I put here? instead of that t. If this has been t minus tau, what should I put in the exponent over there when I substitute this with this Fourier transform? T minus tau, very good. I just replace this with t minus tau. Okay? And then I have a d tau somewhere over here. Okay? And then I can actually perform the d tau integration first by exchanging the order of integration with d tau and d omega. I can exchange the order of integration, which is the same like exchanging the order of summation. Integrals are just summations. So I can bring this inside and rewrite this as 1 over 2 pi d omega, put this in the outside, e to the j omega t. I break this into two terms. Okay, this is e to the j omega t, e to the minus j omega tau. This is just a product of that two things. And then I'm going to leave whatever that does not depend on tau on the outside after the exchange of integration. But whatever I have that depends on tau, I leave it inside the inner integral. Okay, I leave it inside the inner integral. So what is the inner integral that you see now? What is it equal to? The inner integral, can everybody follow going from this step to that step, or you want me to repeat that? Alexander, can you follow? Okay, good. He follows, so most of you will follow, going from here to here. Okay? So what is the inner integral that you notice? It should be the Fourier transform of f of t, or f of tau. You just use a dummy variable tau instead of t that you see in the textbook. Okay? So this is nothing but f of omega. So this integral becomes 1 over 2 pi minus infinity the omega e to the j omega t, h of omega times f of omega. So y of t now has the Fourier transform that is given by h of omega times f of omega. Okay, let me erase this part of the blackboard. So what it says is that yt, which is written as, say, f of t convolving with h of t, okay, it has the Fourier transform of yt is h of omega times f of omega if the Fourier transform of f of t is f of omega, and if the Fourier transform of h of t is h of omega. Okay? Something that is very complicated looking in this integral is just a product in the Fourier space. It's just a product in the Fourier space. This is a very important property of convolution. Something convolving in the time domain, this is called in the time domain, is actually just a multiplication in the frequency domain. Okay. Does everybody get this? You have to remember this. This is the most important property that you need to take out of this course. One of the most important properties that you need to take out of this course. Okay? So, other things that you should know or draw very easily from this property is that order doesn't matter. You can write this first or that first. It doesn't matter. Okay? In the Fourier space, it would just be a product. Order doesn't matter also. F can come first. H can come first also. Okay? Order doesn't matter. And that what happens if you have something like this? that if y of t is, say, f of t convolving with h of t, and then convolving again with g of t. Okay, is this equal to f of t convolving with h of t convolving with g of t? Okay, I can use the same bracket. It turns out that this is true, but let's see how this is true. Okay, let's take this to the Fourier space. Let's assume that, let me call this function f of omega, h of omega in the Fourier space, right? So in the Fourier space, y of omega will be equal to the Fourier transform of this one, okay? The Fourier transform of this one would be just f of omega times h of omega, okay? And then times g of omega. And then if I take this to the Fourier space, this other thing to the Fourier space, it will be f of omega times the Fourier transform of this block over here. It will be h of omega times g of omega. You can see that in the Fourier space, the order doesn't matter. So in the time domain, order doesn't matter also. So that thing equals that thing. Okay, this is called the associative property. In math, it's called the associative property. You have A times B times C equal to A times B times C. This is called the associative property in mathematics. Okay, so this property is associative. And then you have the shift property. Say if I were to shift yt minus t0, okay, what is it equal to? It turns out that this is equal to ft minus t0 convolved with ht, or it is also equal to ht minus t0, since order is not important convolving with f of t. Okay, the two are the same. You only need to shift one of the two players. You don't need to shift both of them. You can prove this property by going to the Fourier space very easily. So if y is being shifted, what happens to its Fourier transform? It will be phase shifted, right? E to the j omega t naught by that much. Okay, we phase shifted. You can see this from the definition of y of omega is equal to dt f of t e to the minus j omega t. Okay, so if you were to change this by t minus t naught, you get a positive phase. What is that? What is that? No, I'm saying that this should be a y, sorry. Okay, this is a y. So if I were to delay that thing, okay, I will put the t minus t0 here, t minus t0, and then put the t plus t0 outside, and then my integrand remains unchanged. So this is a correct phase shift. Okay, this is a correct phase shift. So I can do it more carefully. Y of omega is a Fourier transform of this. Then the question is, if I were to find the Fourier transform of this, what is it? Okay? And then if I were to find the Fourier transform of this, I can change variable and call t prime is equal to t minus t naught, the dummy variable. Okay? So if I do that, then t is equal to t prime plus t naught. Look at t prime plus t naught. And so if I change this dummy variable, dt prime is dt. So I will get this to be dt prime. And then y of t minus t naught is y of t prime. And then here, I will have e to the j omega t is equal to t prime plus t naught. Okay, t prime plus t naught. So then, so the Fourier transform of this is actually equal to y of omega times then e to the minus e to the j omega t naught. So there should be a minus sign. Okay, there should be a minus sign here if I did the math correctly. Okay, so this part will be y of omega. So if I do the time delay, this Fourier transform translates to that. Okay, so if I use this property, then the right hand side would be this thing times e to the minus j omega t naught times h of omega. Okay, if I were to use the first formula, so this is equal to y of omega e to the minus j omega t naught. So both sides are satisfied. Left hand side Fourier transform to this, right hand side Fourier transforms to that. So sorry, I'm missing a, yeah, I'm fine. So it's f of omega, h of omega, e to the minus j omega t naught. Now if I were to take the Fourier transform of this one, okay, it will be h of omega e to the minus j omega t naught times f of omega. It's the same as that one over there. Okay? So you don't have to delay both of them. You just need to delay one of them in the convolution. That is the shifting property. And what about the derivative property? What happens if I need to find the derivative of a convolution? Yes?
So suppose you have two signals, right? F of t and g of t.
Yes.
If I prove that f of omega equal to g of omega, does it mean that f of t equal to g of t?
Yes. Yes. Yeah. Yeah.
Okay. In this case, since f of omega h of omega e to the negative j omega t naught equals y of omega e to the negative j omega t naught, wouldn't you be able to cancel e to the omega negative?
No, I'm saying that this first term Fourier transform to this.
I see.
The second term Fourier transform to that. And if I were to take the Fourier transform on the first line, the Fourier transform to that, and the two are the same. So what I'm saying is that this is equal to that. If you were to time delay the left hand side, you only need to delay one of two players. Okay? So Aditya's question is, if f of t Fourier transform to f of omega, g of t Fourier transform to g of omega. If f of omega equals to g of omega, you have to augment this with a qualifier for all omega. This is a mathematical symbol for all omega on the ray axis. If this is true, okay, this implies that f of t equals to g of t, okay, for all time. Okay, and you can prove this very easily by just writing down the Fourier inverse transform and argue that the two actually are the same. Okay, so let's go and derive other properties. Derivative properties. Say if y of t equals to, it doesn't matter what order I write it in, f of t. If y of t is a convolution of h of t with f of t, then it says that dt is equal to either the derivative of the first term convolving with f of t, or you can have the derivative of the second term convolving with h of t. I can prove this by using the Fourier transform property. If y of t Fourier transform to y of omega, what does dy t of dt Fourier transform to? J omega, very good, J omega, y of omega. Okay, so the left hand side is just equal to that. Okay, where y of omega from the first line we already know. From the first line, what do you know y of omega to be in terms of h of omega and f of omega? It's just the product of the two, right? It's just h of omega times f of omega. This is true from the first line. Let's see if we can prove that the second and the third line are correct. Okay? So, the left-hand side, Fourier transform to this. The right-hand side, the first term, what does the Fourier transform to?
J omega h.
Very good. The first term just Fourier transform to that. The second term Fourier transform to f of omega. So this is what this line Fourier transform to. What about here? The first term Fourier transform to h of omega. The second term Fourier transform to j of omega times f of omega. And they're equal to each other, as you can see. The first line and the second line are the same as each other. So it doesn't matter why you write the derivative operator. You can operate on the first term or the second term. Is this clear? Not soup, right? Or piece of cake.
Now we're using.
So let's do some examples.
What's convolution used for?
Actually, I still have the old exams here. If you haven't picked up your old exam, I still have them. Okay. And another property that I need not have to prove is this other property, distributive properties. Okay, I think it's so easy to prove that you can do it by yourself as well. Okay, that f of t convolving with g of t plus h of t is the same as f of t convolving with g of t plus f of t convolving with g of h of t. Okay, I don't need to prove this. You can prove this yourself. Shifting property I already proved to you. Derivative property I already proved to you. Another one is reversal property. Okay, reversal property. And that you can prove yourself. Okay, I hope I don't have to prove it. If y of t equals to h of t convolving with f of t, then if you were to reverse time, okay, it would just be minus t convolving with f of minus t. That you can prove very easily too, using the Fourier transform property or the direct definition of what a convolution is. Okay. So
Professor Chip,
yes.
do you use convolution for an application?
What do we use convolution for? it is, you wouldn't know right now. It will be difficult for me to tell you right now, but after a while it becomes obvious, okay? It becomes obvious. But let me do an example with you. Let me do this very simple example. Y of t is equal to f of t convolving with a unit step function. This is a unit step. A unit step function. And that by definition, a unit step function looks something like this. 0, 1, and then 0 when t is less than 0. Okay? So if I were to write this out, y of t will be equal to minus infinity to infinity f of tau times u of t minus tau b tau. Okay? And what do I know about the unit step functions? When tau is larger than t, what happens to this function? It's 0. Okay? When its argument turns negative, it's 0. So I don't have to integrate all the way to plus infinity. I know that I need to only integrate up to t, tau equals t. Because when tau is larger than t, this thing is 0. So this convolution can be written as such. And actually, I don't need to write this down because it's just equal to 1. Okay, so this convolution can also be written as such. Okay? And you can also do it the other way around if you want to. When you convolve, order is not important. So I can also write this as being equal to minus infinity to infinity u of tau f of t minus tau d tau. Okay, doesn't matter which one I write first, order is not important. Then I know that this thing I need to integrate only up to when? When tau is 0 to infinity, right? When tau is negative, it's just equal to this. Okay, are these two equal to each other? Are these two equal to each other? Well, you can make them equal to each other by a simple change of variable. I can call this tau prime equal to t minus tau. Then the tau prime is equal to minus the t tau. Okay, then this goes from 0 to minus infinity f of tau prime, the tau prime with a minus sign, and you flip this around, you get minus infinity to 0 f of tau prime, the tau prime. So in fact, they're equal to each other. Oh, sorry. There should be a, this is not 0, because when tau equals 0, tau prime equals t. Okay? This should be t. So the two are, in fact, equal to each other. The negative sign goes from just flipping this around. Okay? Flipping the order of the limits. I get this. So the two are, in fact, the same. So, if I were to use the derivative property of the convolution expression, if I were to find the derivative property of this, okay, and then I will have this ft convolving with dut dt. What is this dut dt? Dut dt is u of t looks something like this. If I were to differentiate it with respect to t, what do I get? 0, but what happens at the 0 point? T equal to 0 point.
Goes to infinity.
It goes to infinity, very good. It goes to infinity.
Direct.
You can think of this. Yeah, it's a direct delta function. You have read ahead, apparently. Okay, so if I define a UA of t that looks something like this. Okay, say this is delta. This is 1. Okay, this is 0. If I define this approximate UA of t to be this function, if I were to differentiate this function, okay, I will have this as my value. It's 0 out here. It's 0 out here. But what is its value in this small interval here?
Slope.
It has a slope of 1 over delta. Okay, 1 over delta. It has a slope of 1 over delta. So this height here is 1 over delta. Okay, this is, let me say, is an approximation to what I call a delta function. Okay, but what happens if we make delta smaller and smaller? It goes to the roof, right? It goes to the roof of this building and up and up and up. You never see it coming back, right? So it goes to infinity if you make delta go to 0. So in the limit, when delta goes to 0, this thing becomes taller and taller and taller. It's called an impulse. It's called an impulse. An impulse is a limiting case of this one. Okay? And what is special about this impulse? Well, what is the area under this impulse? If you were to seek out this area, this width here is delta 1. The area is always 1. That is this special